Let's spend the rest of our time with a system of linear differential equations, not linear algebra equations, but linear differential equations. It's a system of differential equations, two differential equations, and two initial conditions. We haven't really talked about that yet. Can I still solve this? And what interpret it geometrically? That's a very vague kind of statement. What would it mean to interpret this geometrically? Well, let me tell you here in our last 25 minutes of class. There's first the question of how in the world to solve it. It is essentially, in part at least, educated guessing. Okay? This particular linear system of differential equations is easier to solve than the general one, in part because I made the second equation only involve y, not x. It is what's called decoupled from the first equation. There's no x there. I can focus on that equation and think about its solution pretty easily, and then use what I find perhaps for that equation. Yeah, that's going to be the strategy here. We've seen that kind of equation before. Find a function whose derivative is always its opposite, negative of the function. E to the negative 2t, right? Or any constant times e to the negative t. I could write y equals c times e to the negative t. However, instead of writing a c, I'm going to write a y sub 0, or a y naught, if you prefer, because that is the initial condition for y. So based on these two equations, I can say that y is y sub 0 times e to the negative t. I can think about that without thinking about the other two equations because of the fact that this equation is decoupled from the first one. There's no x's there. Now, I could have included x's. I could have had like a 3x minus y there on the right-hand side. Then I could not have done such a thing. And it would have been a lot harder to solve it. There are methods. In fact, that's the main point of chapter 3 in the textbook, is how to deal with such situations. In a nutshell, I mentioned the words eigenvalues and eigenvectors before. That's what we end up using to solve a harder example. And that is related to change of coordinates, skew coordinates. That's not going to come before exam 2, between exam 2 and exam 3. Yeah, take this now and substitute it up here. To get the equation dx dt equals negative 2x plus y sub 0 e to the negative t. What's y sub 0? Well, I haven't told you what y sub 0 is. It's some unspecified particular number. You could pretend it's 10 or something. If it were 10, then there'd be a 10 there. If it were negative 7, there'd be a negative 7. Now solve this equation. It's not as hard as it looks. You've done this kind of equation before, actually. It's a non-homogeneous linear equation. We could use either integrating factors or guessing, method of undetermined coefficients. Should we try both ways to re-emphasize those things? Okay, let's try both ways and see that we get the same answer. Let's try integrating factors first. With integrating factors, you want to try to get the function that involves t by itself on the right side. You want to first add 2x to both sides. Dx dt equals 2x. Oops, sorry. Dx dt plus 2x equals the right side, y sub 0 e to the negative t. And for the integrating factor, you take whatever coefficient of x is. In this case, it's a constant, 2. It doesn't have to be a constant, but it often is. The integrating factor, mu, is e to the integral of whatever that function is. That's a constant function in this case. So in this case, the integrating factor is e to the 2t. You don't need to put a plus c up there because you can always take c to be 0. That's the integrating factor, IF, for integrating factor. Next step is to multiply both sides of the equation by the integrating factor. You would get e to the 2t times dx dt. Don't be bothered by the fact that we're using dx dt instead of dy dt here. Plus 2e to the 2t times x. Don't forget to multiply it on the right side. That's a common mistake, is to forget to multiply it on the right side. E to the negative 2t times e to the negative t times e to the positive 2t is e to the positive t. Why is that helpful? Because if you've done it right, the left-hand side is easy to integrate. That's why. Because if you've done it right, the left-hand side will be the derivative with respect to t of the unknown function x times the integrating factor. I'll write it as the integrating factor times x. X is a function of t. I'm not writing that there, but it is. Keep in mind, x is a function of t. It's not a constant. Right? Check that with the product rule. You differentiate this product. The first function is e to the 2t. The derivative of the second is dx dt. X is not a constant. It's a function of t. Plus the second function x times the derivative of the first. The derivative of e to the 2t is 2e to the 2t. And because of that, it's easy to integrate. Now integrate. I won't even bother writing an integral sign. Just say integrate. The left-hand side, because it's a derivative, integrates to what's inside the derivative expression there. The integrating factor times the unknown function x. We do have to actually integrate the right, though it's really easy. Y0 e to the t is what it integrates to. You do want a plus c here. Don't forget what you're trying to do. You're trying to solve for x. Yeah, divide both sides by e to the 2t. Multiply both sides by e to the negative 2t. X will be, that times e to the negative 2t is y0 e to the negative t. And c times e to the negative 2t is exactly what I just said. Don't be scared off by the fact that there's a y there. Okay, this is how x depends on t. Y0 is a specific number. It's the initial value of y. It can be in there. I do want to still solve for c, though. This is my general solution of this equation. I have this generic initial value problem, though. I do know x of 0 equals x sub 0. I do want to solve for c. X sub 0 equals x of 0. Plug in t equals 0. E to the 0 is 1. You get that. So for c, c is going to be x sub 0 minus y sub 0. So we're basically done with our solution. Let's write the solution as a vector. I'll call the vector capital Y because that's what the textbook does. It is a function of t. Let me go ahead and use my phi notation that I often do in the lectures here. Phi or phi. I say phi, you say phi. Except since it's a vector, I'm going to switch it up. I'm going to use a capital phi because it's a vector. There's a capital phi. Looks like a Mario Brothers squishy thing that they jump on. Capital phi of t. I often do put subscripts here as well to emphasize the initial condition. I won't today. It equals, well, you could write it little x of t and little y of t if you like. And what are those? Little x of t is this thing here. Replace c with x0 minus y0. So you'll get y0 e to the negative t plus C is x0 minus y0, I'll put that in parentheses, times e to the negative 2t. And y, that was the easy one. That was y0 e to the negative t, that we found that back 10 minutes ago. There is the unique solution of the generic initial value problem in vector form. Written as a column vector. You could also write it as a point. And in fact, if you did write it as a point, that in some ways is better in terms of interpreting it geometrically, as I'm about to do. What were the directions again? Solve the generic IVP. That's this whole thing here. I call it generic, by the way, because I don't specify x0 and y0. That's why I call it generic. It is an initial value problem because I've got initial values. I just don't say what they are. In the book, homework problems, task problems, you should be able to handle particular numbers here. It's a little easier. Interpret geometrically. What's that about? Okay, this is perhaps our last 15 minutes of class today. This is perhaps the most important kind of idea for the entire semester here, what I'm about to emphasize. The geometric interpretation of this. In the textbook, it's discussed at the beginning of chapter 2. When you read about vector fields, generalization of slope fields to higher dimensional systems of equations. I also in the lectures talk about something called nullclines. Now the book talks about nullclines too, but not until chapter 5. I think it's good to introduce it early. So I start talking about an idea that you don't find in the textbook until chapter 5 in chapter 2. So I think it's a super helpful idea. It's a little confusing at first, but it's super helpful once you get it. Helps you draw more accurate pictures. So let's rewrite this system of linear equations on the next piece of paper here. And I'm just going to write the system of differential equations. I'm not going to bother with the initial conditions. System of linear differential equations. First order. First order because it involves just first derivatives. Linear because the right-hand sides are linear in little x and little y. First powers, no square roots, no cosines or sines or anything. It's like a linear transformation, maybe. Maybe. Could we write this in matrix vector form? Yes, you can. This system of linear differential equations is equivalent, that's two linear scalar equations, is equivalent to one vector equation, just like we talked about with a system of algebra equations. You could write it in vector form. dx dt, dy dt. That one vector equals this one vector. And you could break this vector apart into pieces, one piece only involving x and one piece only involving y, just like we did half hour ago with the linear system of algebra equations. Factor out the x, factor out the y, and that by definition is the same as a matrix times a vector. Just like with the purely algebra example, no differential equations with the other example. And we could give the matrix a name. We could call it A. We could give the vector a name. We could call it X, but the differential equations book always calls it capital Y. So with differential equations, I'm going to call my vectors typically capital Y. With linear algebra, I'm going to call my vectors little x. I'll put half arrows above them both. That'll be a signal. Hey, this is differential equations, whereas when I use x, it's purely linear algebra. The symbol is arbitrary. And what should I call that thing? How about d capital Y dt? Vector capital Y. Does that make sense? Well, it kind of makes sense. Differentiate this vector. I guess you differentiate each component. Essentially, by definition, there's no magic going on there. That's the definition of what it means to differentiate a vector. And so the differential equation in vector form becomes d capital Y dt equals the matrix A times Y. Can we solve that by multiplying by an inverse matrix? Not really. We're trying to solve for Y as a function of T. I mean, it doesn't really help because you could multiply both sides on the left by A inverse, but then Y would equal A inverse times dy dt, and that seems even more confusing. So while you could do it, it's not really helpful here. We will use inverse matrices for solving these things, though, in a different way, related to change of coordinates and eigenvalues and eigenvectors. That comes after exam 2. What am I trying to emphasize now? I'm trying to emphasize that in geometric interpretation. Okay, we're about to try to sketch in 10 minutes a phase plane and solutions in the phase plane. What is the phase plane? Give A times Y another name. I could call it T of Y, thinking of it as a linear transformation. The textbook, though, more typically calls it F of Y. And in fact, the capital F that I'm using here also is bold-faced in the book. By hand, I'll put a little half arrow above it. Is that a linear transformation? Yes, it is. However, in the differential equations here, we're not going to really think of it as a linear transformation. Instead, we're going to think of it as a linear vector field. Maybe you've heard that phrase before, vector field. Maybe in learning about electromagnetism, electromagnetic lines of force, that kind of thing. You might have talked a little bit about vector fields with surface integrals and what Gauss's theorem and things like that. Maybe that brings back nightmares or something. Gen Physics 2. Vector fields are talked about a little bit there, though you may not really remember much. What is a vector field? A vector field is a function that takes a vector input and gives a vector output. In this case, it is a linear function. It is a linear transformation. But you can create nonlinear vector fields as well. The key thing is it's got vector inputs and vector outputs. And we can visualize it not as a mapping as we do with linear transformations, but as a vector field. In the plane, you draw a bunch of vectors. What vectors? And I'm not going to draw a vector here, but at an arbitrary point, here's the idea. You plug that point, you think of the position vector of the point, you draw it, so to speak. You imagine plugging that vector in here and getting a vector out. What vector? Well, do that computation there. That's what vector. It's this vector, actually. And you draw that output vector to have its tail at the point you plugged in. Do that for every point in the plane. Infinitely many points. Of course, nobody can literally do such a thing, not even a computer. So we settle for drawing it for finitely many points. And you get a bunch of vectors and you can get kind of a messy picture. But oftentimes, if you shorten the vector, you get kind of a pretty picture, actually. What's the quickest way to sketch the vector field without a computer? Think about what I mentioned are called nullclines. What are nullclines? You set the right-hand sides of the system of differential equations equal to 0. Null in nullclines means 0. If I set this equal to 0, those equations set equal to 0. Ignore the differential equations. Just focus on the algebra. Define, well, lines in the plane. The line, this one's the line y equals 2x, goes to the origin with a slope of 2. This one's the line y equals 0, which is the x-axis. The x-axis is where y equals 0. Let me draw those lines in here. Y equals 2x. And the x-axis is y equals 0. Now go back and think about the differential equations. The first nullcline, where the first right-hand side is set equal to 0, y equals 2x, is a line in the plane where dx dt is 0 along solution curves. If a solution curve, and I haven't really explained what solution curves are, they are, other than, I'll just say it now, they are curves in the plane. If a solution curve touches the x nullcline, dx dt has to be 0. What does that mean? That means the solution has to cross it with a vertical tangent. The x component of the velocity of the solution curve has to be 0 there. What did I just say? Velocity of a solution curve? Yeah, I did just say that. And for the y nullcline, dy dt has to be 0. The velocity of the solution curve, so to speak, has to be 0. 0 y component. It's got to cross it horizontally. Think about this one. Dx dt is 0 along that line. The horizontal component of the velocity of a solution has to be 0 along that line, meaning solutions have to cross this line with vertical tangents. Zero component in the horizontal direction. The other one has got to cross with horizontal tangents. But the other one happens to already be horizontal. So it doesn't, the solutions don't really cross it with horizontal tangents. They actually have to stay on it. Think about the formula a little bit here. There's your generic solution of a generic IVP. Notice you got a bunch of exponential decays in there. As t increases, those go to 0. All solution curves for this particular system have to have x and y coordinates that go to 0 as t goes to infinity. In this picture, that means they have to be approaching the origin. Make a big dot at the origin. In fact, if your initial condition is the origin, if x0 and y0 are both 0, then these are always 0 no matter what t is. Everything becomes 0. The origin stays where it is. It's an equilibrium point, just like an equilibrium point in a phase line, but now it's an equilibrium point in a phase plane. And all the other solutions have to go toward it as t goes to infinity. And I'll just draw some other ones in without explaining, other than just showing you that they go toward the origin, and they do have to cross that x nullcline with vertical tangents. I'm not really explaining it beyond that. This is a partial picture of the so-called phase plane for the system of linear differential equations, showing the behavior of the solutions is to go towards 0 as t goes to infinity. I mean, you know that from the formula anyway, but this is showing the way they go to 0. You might protest a little bit here and say, hey, wait a minute, aren't these things failing the vertical line test? How can they be functions? They are functions because they don't have to pass the vertical line test. these are not y as functions of x. They're x and y as functions of t. They're parametric curves, which you should have learned about a little bit in calculus. Functions of t. Where's t in the picture? T's in your mind. You're imagining t. You're imagining moving along the solution curve as t increases, or solution curves. T is all in your mind. Okay. This is a phase plane for the system of linear differential equations, and it is, in a sense, a sketch of the vector field as well, without literally drawing vectors. Basically, the vectors have to follow these curves because the curves have to be tangent to the vectors. So I didn't literally draw the vectors like I mentioned a few minutes ago for the vector fields, but I could, based on this picture, I could try to draw like vectors that look like this, for example, that these solution curves are tangent to, just like in a slope field. These are hard concepts to learn in 25 minutes. I'm just introducing it, okay? But it's very important for this class. Have a good day.